Okay, so today I would like to show some decidability results about monadic second-order logic that we discussed last time. So I will remind you in due course what monadic second-order logic of order is. But let me first talk to you about automata. So we've seen automata many times in many talks, and some of you are very familiar with them, obviously, and some of you have never seen them. I will just give some examples of automata. Of course, there is a formal definition. You have a set of states, you have an alphabet, you have a starting state, a transition relation, and most importantly, what distinguishes the various flavors of automata we have, it's the acceptance condition. So automata can accept either finite words or infinite words, and when you accept infinite words, there are various ways in which you can do it. So let's try to design first an automaton over an alphabet A, B, and C. And so I want an automaton A such that the language of A, so the language of A is a set of so it's the set of infinite words here that A will accept. So the set of W in sigma to the omega such that, and I want to say that I'm going to write it informally, so every A is eventually followed by a B. Let me do this, otherwise it gets confusing, doesn't it? Okay, so I'd like to, it's just an example. I mean, I know some of you are, it's a very baby example for some of you, but this will help, just put in some notation and give an example. So how would you design such an automaton? So you want infinite words, but whenever there's an A, eventually at some point later there has to be a B. So let's have a look. So I'd like to, so I'm going to write some things, and I'll explain notation afterwards. So here I've got a state. I will have a self loop, and the self loop will be adorned with the letters B and C. Okay, and now I have a transition where I do an A, and here I can do, let's say, an A and a C, and when I do a B, I come back here. Okay, so I've written something. So you have two states. So an automaton has got a finite number of states or control locations. So the two states, I haven't named them, but they're here and here. This one is the start state. That's indicated by this incoming arrow. And it is doubly circled. So that is a so-called accepting state. Okay. Now, in order to accept a word, so you're given a word, and the automaton will eat this word and follow the arrow according to what the next letter in the word is. Okay, so if you give it a word, you start, what is the first letter? If it's a B, you self-loop. If it's a C, you self-loop again. This B, C means there are two arrows, one with B, one with C. At some point you see an A, you go there. Maybe you see some more A's, then you take a B. And the accepting condition, it's a Büchi accepting condition. Büchi accepting condition. The Büchi accepting condition means in the infinite sequence of states that you visit as you accept this word, you have to see at least, there has to be at least one of these doubly circled accepting states that is seen infinitely often. That is the condition. Okay? You cannot at some point not see an accepting state. These states are called accepting states. So first of all, does this make sense, this definition? Any? Okay, so it's clear. Do we agree that this automaton meets the specification? Yeah, do we see this? So this automaton will have a bunch of B's. Whenever you do an A, so here you're in accepting state. At that point, you've not seen an A, and therefore you'd be quite happy to accept and just keep doing B's and C's for the rest of your life, because by vacuously this would hold. And if you do an A, you come here, now you can do several A's. We didn't say that there was a one-to-one matching between the A's and the B's. We just said eventually you must see a B. And when you see the B, you come back to your state where you say, now I'm square. Okay? Okay, so this is good. Let's have another one. The language will be 0 and 1. You have to, when you look at the sequence of states, you got a word, and the word will induce it's a condition as to whether the automaton accepts the word or not. So L of A is the set of words that are accepted by A, accepted by the automaton. Yeah. So here's another example. So now the alphabet is different, 0, 1. And I want to say, I want an automaton A such that the language of A is, so the set of words in 0, 1, such that there is only 1, 1. Okay, and so that's a fairly easy automaton to have. So I start here. I don't know, so I can do zeros here at some point. So there is exactly. So you need to see exactly 1, 1. So at some point you have to see this one. And once you've seen this one, you're happy to accept, but you cannot see another one. So we'll just put a 0. So you start here. You see a bunch of zeros. At some point you need to see the 1, and then you say, now I can accept, and I cannot see any other one. Okay, does that make sense? Okay, and then finally, I want to have an automaton, again over 0, 1, such that the language of the automaton is the set of words such that W has, so infinite words, okay, has finitely many ones. Okay, yeah. Yeah, well, we could, or maybe we don't. So I'll come to that in a second. Yeah. Here we're saying, for instance, what happens if the word has a 1? But so here in the implicitly, what would happen is that you cannot proceed further. So that word would not be accepted, because in order to accept, you have to be able to read the whole thing. But also, an alternative is you could have a sync state, where when you see a 1, you go to the sync state, and that sync state is not accepting, and from that point on, you can do whatever you want. So there are several ways to deal with this. Thanks. So here you have an automaton that has only finitely many ones. So how could we do this? So we can have, let's see, you can have a bunch of zeros, and then you have a 1 here. And now you, what am I saying? No, that's not what I want. You can have a bunch of zeros and 1s, and eventually you want to take, you've seen the last one that you're ever going to see, so you take a 0, and from here you just do zeros, and you accept. So initially, you can do however many zeros and 1s you want, but at some point, if you're going to accept, this is an infinite word, you have to cross the, cross that bridge here, go into this region of the automaton where you cannot accept any 1 anymore. You can only accept zeros, and therefore it'll be only finitely many 1s by construction. Is this okay? Yeah, very good. So these automata, the first 2 are deterministic. The first 2 automata are deterministic. That means whenever you see a letter, you know exactly where you are. Okay? This one is non-deterministic. That's actually annoying. And there's an entire research area, well, I guess now, I don't know if there are still papers, but for many, many years, determinizing Büchi automata. That's like, you wouldn't believe the number of papers now. It's also extremely complex. I mean, the algorithms are crazy complex, some of them. This is a non-deterministic automaton. Could we get a deterministic automaton to accept the same language? Or finite words, yes, because we can determinize finite automata. So the answer is no, you cannot, and I'll just give you intuitively the proof. So suppose you had an n-state automaton, deterministic n-state automaton that accepted the language accepted by this automaton. So n state here, this is a two-state automaton. So an n state would have, if you have a deterministic automaton, you'll have n states, right? And now you would look at the language, let's see, you would look at something like, you would look at 1, 0, 0, and now you have n plus 1 zeros, and you repeat this forever. Sorry, not a language, sorry, that's a word. Okay, now this word, is it accepted by, is it in the language? Should it be accepted by the automaton? No, right? It has infinitely many ones. However, the automaton, my putative deterministic automaton that accepts it, has n states. So when I'm reading this part, by the pigeonhole principle, it has to be the case that as I'm reading this, this word, I'm reading, all these zeros, and I have to visit the same state. I have to visit the same state twice. Okay. Now, of course, it's deterministic. So that means that if instead of having this word now, all of a sudden I change my mind and I say, you know what, from now on, I'm just going to have infinitely many zeros, that word should be accepted. But what will this word be? Well, if I went from 0 to 0 and I was in Q and I ended up in Q, then at that point, I will, because it's deterministic, I will still have to visit Q here, I have to visit Q here, and I have to go through exactly the same sequence of states, right? Because it's deterministic. That means there has to be an accepting state somewhere along the path, because I have to accept this thing, and I have to see an accepting state infinitely often. So somewhere on that path, which repeats, I have to see an accepting state. Is everybody with that? Agree with that? Okay, and now I change my mind back again. I say, you know what, never mind. I'll go back to the original word. So I put a 1, and I put a 0, and a 0, and so on. And then I put a 1, and put a 0. I go back to this word here again. Now, it's not necessarily the case that I will see the same pattern here in this segment as I do here, because in this segment I had only seen a single one. Here I have seen 2 ones. Maybe the automaton remembers this. However, there must be 2 states that are the same by the same pigeonhole argument. It's going to be maybe Q prime. And by the same argument as before, that must have an accepting state, because I could play the same game. Okay, and then I can do it again, and there's going to be a Q, there's going to be a Q double prime that I visit twice with another accepting state along the way. And I repeat this, and now you look at this word, well, I visit an accepting state, and an accepting state, and an accepting state, infinitely often. So I have a contradiction. I would actually accept this word, but I'm not supposed to. Okay, however, there is a deterministic automaton that does accept this language, yeah.
So accepting is just visiting any visiting accepting states.
So to accept, there has to be a run, some run. There could be many. If it's non-deterministic, you're going to have many runs. There could be many runs, but there has to exist at least one that when you're on that run, you look at the set of states, the sequence of states that you visit, and there has to be an accepting state that you visit infinitely often.
It's the same one?
Well, yes, the same one. There are finally many accepting states, and there has to be one of them you visit infinitely often. Yeah. So now there's a way to actually have a deterministic automaton that captures this language. In fact, that captures any omega regular language, but you have to change the acceptance condition. I will just briefly, I won't obviously give a proof. This is a very difficult proof, but so Müller automata. So you change the acceptance condition. It's not very difficult, but I will just give you an example. So the way you would accept that language is you have here, you have a state Q0, and you do a 0, you do a 1, Q1, and here you do a 0, and now you do a 1. And the accepting condition, so this is a Müller accepting condition, is Q0. I'll explain what this means. OK, so this automaton is deterministic, because whenever you read the letter, you know exactly where you are. And the acceptance condition here is different from the Büchi acceptance condition. The acceptance condition says that in any infinite run, the set of states, the whole collection of states that you see infinitely often has to be exactly that set. So I have to see Q0 infinitely often and no other state. I cannot see Q1 infinitely often. So by construction, this works. You might think it's a bit of a cheat. What's actually nice is that Müller automata can be determinized. You can always have a deterministic Müller automaton that can always accept any omega irregular language. Okay, so that's for automata. Any question on this? Yeah? Yes, a Büchi automaton is always a Müller automaton, correct. However, well, you can always take a Büchi automaton and just translate the acceptance condition into Müller. That's very easy. Every Büchi automaton is a Müller automaton, if you will. But conversely, there are Müller automata that are not Büchi. Yeah. Yeah.
What is the definition of an omega regular language?
Accepted by a Büchi automaton or a Müller automaton. So if the Büchi automata I've defined. Non-deterministic Büchi automata. Or equivalently deterministic Müller automata, but I've not exactly told you what a Müller automaton is. But the Büchi automata, I think it's well, I haven't completely formally defined it, but I think it's correct. Correct. That's an omega regular language. By the way, a regular language, that's going to come up in a sec. A regular language is over finite words. A regular language means you're accepted by a finite automaton. All that means is you have to end in an accepting state. So you're traveling, you're eating the letters, you're visiting states. You don't have to end when you hit an accepting state. You can pass through an accepting state, but one thing's for sure, eventually when you do want to stop, you have to be in an accepting state. Those are regular languages. Yeah?
I think I missed it. Could you repeat the point of discussing the Müller automata right now?
They can always be made deterministic. Which in a sec I will somehow. Oh, the proof of that is difficult. Yeah, I cannot give the proof of that. Yeah. I mean, just complementing Büchi automata is complicated, but yeah. But we'll see. Yeah.
Itself is not deterministic.
Sorry.
And this example is not deterministic.
So the one on the left is not, because when you take a 0, you can either do a self loop or. That one is deterministic. But I haven't proven you can always do it. I've just said, hey, here's one that's deterministic that does it. No, it's something.
Maybe because, so I think the claim is that this language is omega regular because it's recognized by this Büchi automaton.
Yes.
However, it cannot be recognized by a non-deterministic Büchi automaton, Büchi, but it can be recognized by Müller.
By deterministic Müller automaton. Yeah.
Thank you.
Yeah. No, thanks for your questions. Let me just see if I want to. Okay. So let me continue. So now I want to do the following. So remember that MSO. I have the syntax, and I can write things such as, x is less than y, or x belongs to capital X. So this is an integer. This is a set of integers. I can write phi1 and phi2. I can write not phi, and I can write there exists x such that phi. I can write there exists capital X such that phi. This is the syntax of MSO, if you recall. And this is enough, by the way. You say, oh, you don't have disjunction, but if you have negation and conjunction, you have disjunction. Oh, you don't have universal quantification, but if you have negation, again, you have. So this is kind of sufficient for MSO, okay? And we saw many examples of MSO and the power of MSO. So now I want to show you that this is a decidable theory. I want to show you that if I give you a sentence in MSO, you can decide whether it's true or false, okay? Sorry, I forgot one last thing I forgot to say about automata, which I will need. Suppose I give you let A be a Büchi automaton. Oops, automaton. Then I can decide if it accepts some words, if it's not empty. So if the language accepted by is not empty. So in other words, I can decide whether there's some word W, infinite word, such that A accepts W. Okay, so how would you do this? Intuitively, it's quite straightforward. So what's a Büchi automaton? You've got all these states, and then you've got these arrows and so on and so forth. And forget even about the labels, the actual alphabet. I just want to keep track of the skeleton structure, just the arrows. So I've got arrows, and so on and so forth. Okay, and I can assume, and some states are accepting, and some states are not, and then I start somewhere. Okay, and it's non-deterministic, so maybe from here I can go there or there. I don't. Okay. So I need to decide whether there is an infinite path in this graph that visits one of these two states infinitely often. Okay, that's what I need to do, right? And that you can do. You decompose it into, I'm not going to write it down, but it's kind of obvious. You decompose it into you decompose the finite graph into strongly connected components. And you need to check whether there is a strongly connected component that has an accepting state. And you need to check if it's reachable. So if you can reach a strongly connected component that has an accepting state, then the answer is yes, the language is not empty. And if that's not possible, now you can never reach a strongly connected component that contains an accepting state, then the answer is no. Okay? Simple as that, very simple. And there are very efficient algorithms to do that. Okay, so here we are. So theorem. So this is Büchi 62. MSO is decidable. Okay, so so I'm going to prove this by structural induction. So what I'm going to do is I'm going to say, imagine you have a formula with free variables, the little x and big X. So here, little x is simply a vector of variables x1 up to xn, and big X bar is a vector variable x1 up to xm. Okay, so I have a free formula. I have a formula with free variables, because if I want to do a structural induction proof, I have to allow myself to have free variables. I cannot just have variables that are I can only have formulas that have no free variables. Now I'm going to, given such a formula, I'm going to define an alphabet, and my alphabet is going to be 0, 1 to the n plus m. And the convention here is that if n plus m were 0, in other words, if there were no free variables, this by convention is simply a singleton's set. Okay, so just in case you're wondering what the 0. So I'm going to define this alphabet, and now what I'm going to do is so intuitively I should explain what this is. So intuitively, what is 0, 1 to the n plus m? So you have a word. A word now is going to be composed of tracks. So you have, let's say, what is it? N tracks, and then you have m tracks. So what is a letter? A letter is simply you go vertically, and then maybe you have 0, 1, 1, 0, 0, 1, 0. Okay, so that's a letter, and the word is simply this collection of letters, infinite collection of letters that go on forever. That's kind of the picture, right? So an omega word in this alphabet there will consist of letters of that nature. Now the idea is that these guys, the n tracks here represent variables. So how do I faithfully encode that a variable has value 17? Well, I will have in position 0, a word, implicitly there's a position, right? Position 0, position 1, position 2, position 3, position 4, etc. If I want to say that variable x1 has value 17, I will have zeros. I will have a 1 in position 17, and then I will have zeros. I'll have zeros before, I'll have a single 1, and I'll have 0. And I want an automaton to enforce this. So one of the things the automaton has to be able to do is to say, by the way, on each of these tracks, there has to be exactly a single 1. But we saw an automaton that could do precisely that. Okay? Now, what about the sets? Suppose I've got the set of powers of 2. So the set of powers of 2, for instance, is the set. So I begin at 0. So it's going to be 1, 2, 4, 8, 16. So now I can view this word as, this set as a word. And what is this word? So I've got position 0, position 1, position 2, position 3, 4, 5, 6, 7, 8, 9. What is the word in question? So the word in question that represents this set, the word in question is the following word. It's a word that says, no, 0 is not a power of 2. 1 is. 2 is. No, yes, no, 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 yes, no, etc. So now I can see how a subset of natural numbers corresponds to an infinite word over alphabet 0, 1. Okay. So when I have a set, if I have, say, x1, and I want to say x1 is a set containing certain numbers, I simply need to ensure that where I want my numbers, I've got 1s, and where on the corresponding track, which would be the first track of the m tracks. And when I don't want the number, I have a 0. Does that make sense? OK, so now that I've set this up, I have a formula 5xy, and I want to say that I can construct, so there is, but I will construct it. There is a Büchi automaton a sub phi, let me call it m such phi, such that for all a comma a in sigma omega, a comma a is in the language of m sub phi, if and only if, when I take my formula phi and I substitute for little x the a and for big X the capital A, then that is true. OK, let me just go through this again. For any, so this is, remember my alphabet sigma. My alphabet sigma is 0, 1 to the m plus n. So now words are, infinite words are tuples in the corresponding letter. So I'm going to write a word as, I don't want to be writing, yes, no, I do want to be writing this, yes. I've got a bunch of numbers here, and I've got a bunch of sets here, okay? And I'm saying those guys, they live here because they've been encoded in the way that I've described. And I'm saying for any choice of such numbers and sets, this word is accepted by my automaton if and only if the formula, when this formula xy, when I substitute little a for little x and big A for big X, then that formula is actually a true formula. Yeah?
So actually, to prove the decidability of MSO, you want to say that there's an algorithm which the formula
Yes.
can
Yes.
compute
Yes.
such an M.
Yeah. Yeah. Yeah, yeah. So here, when I say there is a Büchi, I'm in fact going to show how to construct it. And now how do you construct it? You construct it by structural induction. So let's do this. Oops. So let's construct it by structural induction. So by structural induction means I look at all my formulas and I have to show, I have to suppose that I've been able to construct it, and then for the subformulas, and then I show how to combine them. So for instance, the first formula we have is x less than y. So this is, there's no sets, it's just x and y. And what does this mean? Well, it means that I have just two tracks, and I have these tracks, there's a bunch of zeros, and at some point, there's a 1, there's a bunch of zeros, and then there's a 1, and afterwards there's, a bunch of zeros and a bunch of zeros. That, for instance, could be an instance of a word, okay? So I have to accept I have to build an automaton that will accept precisely those words where the one that occurs in the first track comes strictly before the one that appears in the second track. Okay, so I have to build such an automaton. Can this be done? Right, now that we have seen these examples, of course it can be done, right? I mean, I can ensure that the tracks are all of the right kind, that you never duplicate the one, and so on and so forth. So clearly, I can build such an automaton that will accept all such words in exactly those words. Okay, so I'm waving my hands, but it should be clear, I hope. Any questions on that, in case it's not clear? No. Okay, good. Okay, so what do I have next? X belongs to X. So here again, I've got only 2 tracks. I've got a track for little x, and I've got a track for big X. Yeah.
So it's clear that for Büchi, if you've got 2 Büchi automata, you can accept the and the ors of the languages. You can construct Büchi automata.
Well, we're not there yet. We're coming.
But you're kind of implicitly using it for x smaller than y because you want basically you want.
Ah, yes. Okay. But this, I'm just saying that if you sit down in 5 minutes, you're going to come up with the right automaton just from scratch, not even knowing what you knew, just because you know the tricks. But we'll do the formal end. Okay. So what about this? Well, here I've got a variable, so I will have a bunch of zeros, and then I'll have a 1, and I'll have a bunch of zeros. And here, what do I have? I have a set, so I could have maybe a bunch of 1s, a set, a bunch of 1s, a set, etc. Would this be a word that I want to accept? No, because it says that x is equal to 0, 1, 2, 3, 4, 5. It says x is equal to 5, but 5 does not belong to my set. So I'd want to reject this string. I want to accept all the strings where the unique one that appears in the top track also has a 1 in the bottom track. And there could be arbitrarily 1s elsewhere on the bottom track, right? Again, I can construct such an automaton. I mean, it's a little exercise, and it's very straightforward. Okay, so that I've been able to do. Now I need to show, how, suppose I've got phi 1 of x bar and phi 2 of y of, let's see, let's just have the same variables. And I need to show, so here I've got an automaton by induction. I've got an automaton a phi 1, and I've got an automaton a phi 2, and I want to build one for the conjunction. So I want an automaton a sub phi 1 and phi 2 that will accept all the words corresponding to that formula. And this is an intersection construction. Okay, so you have to do a product construction. So essentially, what is this product construction? I'm not going to do it. You have to run the 2 automata in parallel. You're running 2 automata in parallel. And there's just a little subtlety. You have to make sure that in the intersection, the word is accepted by both. There's a unique word that needs to be accepted by both. That's the whole point of intersection. So you're running the same word on these 2 automata in parallel. And now the idea is that you need to keep track of when this guy accepts and when this guy accepts. When I say accept, is visiting and accepting state. They don't necessarily visit accepting states at the same time. But finite automata can always be assumed to have access to a finite amount of memory. You encode this in the state. So you can always assume that a finite automaton has got like a register that has finitely many values. So what you do is this. You imagine you have these registers. And then you say, whenever you visit an accepting state, you say, now I remember this guy's visited. You wait for this guy to visit an accepting state. And eventually it does, OK, now both have visited accepting states. And you reset. And when you reset, you visit an accepting state here in the new automaton. And you ask that you do that infinitely often. This is the key thing. You want to visit that accepting state infinitely often. That ensures that you visit in the first one and the second one. The first one, the second one. Every time that happens, and you keep track of that. OK, so I won't do the construction. Now we have negation. I will do negation in a second. We have existential quantification. There exists x phi of x, comma, let me do this, y bar, comma, x bar. So now I've split my x bar as little x and then y bar, and this guy doesn't change. So I've got this formula here. How am I going to do that? So again, I assume I have a formula. I have an automaton a sub phi that can handle this. Now I want an automaton a sub exists x phi that does this guy. How would I do that? Those of you who have not seen it, there are world experts on this stuff in the room, like you. Any idea? If you've never seen this, kind of, how would I do that? Anyone? Yeah? Yeah.
If you try just to you list the number one after another one, you have 0 at 0, 1 after 2, 1, and so on. You list all the number, and then sometimes you will have you will detect if there is one number.
Okay. So I'm not quite sure if this is Julien. Yeah.
So the new automaton will read one track less.
Yes.
And so it has to simulate that track.
Yes.
For each state in the new automaton, you will have arrows that correspond to the case where you read 0 in that track.
Yes.
Where you read 1.
Exactly.
You replicate this
Exactly.
case or
Exactly. Yeah. So it's a projection operation where essentially you take this automaton. This guy will have one track less because there's one variable less. So the alphabet has now changed. Okay. This is over. The alphabet here has got the letters have got they're n plus m. This is n minus 1 plus m. Okay. So you got one track fewer. And what you have to do is you essentially erase. You need to erase the ones and the zeros from so the letters here. You erase the value of x, whether it be 0 or 1, in the transitions. In the transitions of this automaton, you sort of erase. You transform letters over n plus m, alphabet n plus m, to letters over alphabet n minus 1 plus m by simply erasing the first component. But you keep the arrows, you keep the structure. And so it's an existential, it's a projection. And this is how you get existential quantification. Because there is a path with, there is a valid path here, if there was a valid path there, but you've erased what the actual value may have been. Yeah?
But don't you need for the thing you erased to have only one?
Yes.
Only 0, so
Yes.
you take that into account, right?
Yeah. You need to take that into account. Absolutely. So that needs to be by a duplication. So basically the way you do this is you're very clever. So I mean, the people don't necessarily have never seen this. So what happens is this: you have a first automaton where you haven't seen the 1 yet, and then at some point there's this idea that you see the 1. You go into a state where now you've seen the 1, and you cannot see. You can only see zeros from there. In that you still erase the thing, but now only the 0 transitions are allowed. And then you use the kind of disjoint kind of composition. I mean, you take the union of the set. These are disjoint copies and so on. It's not an intersection. It's just a kind of a union sort of thing. Yeah.
Isn't there another way to do it by using the fact that so you know that there exists x such as phi if I'm only m phi has an accepting state, then you use this like here that you can decide if m phi has an accepting state. It is decidable, but not only is it decidable, but there's an automata which can take into input an automata and find if there's a connected.
I'm not too sure, because I'm not completely sure I understand the construction you have in mind. But let me just continue, because but certainly I think this projection thing, which is kind of canonical, works. I hope people are convinced. Okay, so this requires a little bit of, there's some subtleties to think about, and I think some of you have put the finger exactly on them. And now I am almost done. I mean, this is the same thing, except you don't even have to worry about there being a unique thing, because with this exists x, it's fine. You can have arbitrary, so there's not even a condition. So that guy is fine. How do I do the negation? And so for the negation, oops, for the negation, I need to complement my automaton. So let me just formally, oops. Let me just formally state that. So I have an automaton A. I have the language of A. And what I want to do is I want to construct an automaton AC, C stands for complement, such that the language of AC is all the words minus L of A. So the complement of L of A over the set of all words, okay? And again, sigma is you know, whatever my alphabet is at the moment. Yeah, somebody was it?
That's not exactly what you want to do because you want to recognize words that properly encode variables.
Yeah, but if you assume that L of A, so you've got the formula phi, and you assume that A phi is the automaton. You assume that A phi is the automaton. Yes. You're right.
Except when there are two ones.
Yeah. Very good. You need also to and condition that variables are properly represented. Yeah, thank you. Yeah, absolutely. Yeah. So the point is, it's not quite right because in sigma sigma to the omega, I have some words that are illegal words. Words in which the variable x has got two ones. So those are not allowed. So I have to, this automaton has to take account that variables are properly represented, that there's only a single one for all the tracks that meant to correspond to variables. I'm going to leave this there, but it's wrong. Thank you. Okay, so now how do I do this? So I'm just going to now do this complementation construction because afterwards it's just a question of hard coding these extra constraints. So what I want to do is show you that Büchi automata can be complemented, and so let me just erase this. So the way you do this is you define an equivalence relation tilde an equivalence relation on Q. So here Q is the set of states of no, what am I saying? Whoops, sorry. On W in sigma plus, I think that's what I want to do. Okay, sorry. I want to find equivalence relation on sigma plus. So what is sigma plus? This is the set of all finite words over sigma. And I want to say that V is equivalent to W. This equivalence relation, by the way, is very much tied to the automaton A. So V is equivalent to W. So if and only if, when I go, if and only if for all P and Q in my set Q, so this is the set of states of the automaton. Q is the set of states of the automaton. For all PQ in big Q in the set of states, so for all two states P and Q, I have that from V, oh my God, I can go using V from P to Q if and only if I can go using W from P to Q, and so I can do that, and I can go using V visiting and accepting state from P to Q, and I can go with W visiting and accepting. Okay, let me unpack this. I'm defining an equivalence relation on finite words, and I'm saying that for any, so what does it mean that two words V and W are in this equivalence relation, are equivalent? I require that for every P and Q, every states P and Q, if you can go from P to Q in the automaton by reading the word V, then you should be able to go from P to Q in the automaton by reading the word W and conversely. And moreover, if you can do so whilst visiting and accepting states, you should also be able to do so by visiting and accepting states and conversely. Okay, so it's easily seen that this is an equivalence relation. And so the first claim is that tilde has finitely many equivalence classes, and each class is a regular language. Okay, so to see this, suppose I have a state, suppose I have a, suppose that Q, I'll do proof by example. Suppose that Q has got 3 states, Q1, Q2, Q3. And so I want to know, can I go, and I've got a word V in sigma plus, okay? And I want to claim that V, that there are only finitely many equivalent, there are only finitely many equivalence classes. So I'm going to describe the equivalent class of V, and then through this construction, you'll see that there are only finitely many. So I have my states, let's say, Q1, Q2, Q3. And here, Q1, Q2, Q3. And have this little grid. OK. And I ask, following V, can I go from Q1 to Q1 following V? Yes, no. So maybe it's a yes. From Q1 to Q2, no. Q1 to Q3, I don't know, yes, no, no, yes, yes, no, no. OK? So that somehow tells you, from P to Q, I've looked at all P's and Q's because I'm assuming I've got only 3 states. I'm looking at all the different possible patterns. I have to do the same, by the way, now for visiting accepting states. So in principle, I should not have like a 1. I should have 1 for the first relation, and then also a different bit for the second one. So here, really, there are 4 possible values. 4 possible values. Let's ignore this.
So following V, meaning making at least 1 move?
Yeah. So you've got your automaton, and you've got Q1, and you've got, let's say, Q3, and the automaton has got, it's got labeled arrows, and now you're going to follow V in this graph, and you're asking, is it possible to follow V from Q1 and reach Q3? If it's possible, then I would put Q1, Q3. I would put a 1 here.
But no, I'm asking about the diagonal Q1, Q1, Q2, Q. So
But Q1 would be. Yeah. So it's in sigma plus. You have to take at least 1 transition. Yeah, sigma plus is at least 1. Yeah. Sigma star is finite, but sigma plus is at least 1. Yeah. Does that make sense? Yeah.
Each what is a regular language?
Each equivalence. Ooh. Each equivalent class. Yeah. Each class. Yeah. Okay. Other questions? Okay. Is this convincing? Yeah. Yes, just the finiteness. So the finiteness, so the argument is that I'm saying the only thing you have to know to determine the class is this matrix, and then the other exactly identical similar matrix that corresponds to that part. So obviously there are finitely many such matrices, right? There's going to be, okay. So there are finitely many such matrices. Now why is it regular? That's a good point. If you take the automaton, the set of words that can go from Q1 to Q1, that's a regular language. The set of words with at least 1 letter. The set of words that can go from that are not able to go from Q1 to Q2, it's a regular language. It's a regular language. And then you take the intersection of all these regular languages. So you have to believe that in a finite graph, labeled graph, the set of words that can go from one node to another is a regular language. It could be an infinite set, of course, but it's a regular language. Okay? And that follows almost immediately from the definition of regular language, which is you're accepted by a finite automaton with accepting states. So it's a regular language. Now, I need a second result. OK, so 2. So for all w in sigma to the omega, there exists equivalent classes LU and LV such that W belongs to LU, LV to the omega. Okay, so I'm saying take any infinite word, whether it's accepted or not by the automaton, and I'm saying that actually this word, there will exist equivalence classes. I have finally many equivalence classes. I still have my automaton there, but I have finally many equivalence classes. So there will exist equivalence classes LU and LV. So this is represented by U, and this is represented by V, such that W belongs to LU followed by LV to the omega. Okay, so how do I do this? So if I look at my word W, let's say I write it as W0, W1, W2, W3, W4, so on. Now, what I will do is, in going from W1 to W3, so here I have the word W1, W2, W3, and so this will be the equivalence. Okay, so let me just write this way: W1, W2, W3. So between every pair of letters, I will actually attach an equivalence class. So in this way, I can think of turning n into a colored, a full colored graph over finitely many colors. So how do I do this? So I've got the natural numbers. So I've got all these elements, and between any 2 points, I will have an edge. And what is it's a directed edge. And what is the color of this directed edge? Well, if this point is 1 and this point is 3, then it will be this particular equivalence class. So I have finally many colors because I have finally many equivalence classes, and I am coloring the edges between any 2 pair of natural numbers by the equivalence class that corresponds to the word going from the first number to the second. Okay, does that make sense? It's a bit of a construction. It just needs to wrap your head around it. Okay. So now what do I have? I have n. I have everything. I've got finite number of colors, and I have arrows between any 2 points. I can invoke. What can I invoke? I want to get a monochromatic clique. Higman? Okay, so I know it as the infinite Ramsey theorem. But I mean, probably there are many. So the infinite Ramsey theorem tells me that there is actually a monochromatic infinite clique. Okay, so there's an infinite subset of n, such that so what does this correspond to? This means there's an infinite subset of I'm just going to use another color. There's an infinite subset of n, such that in this infinite subset, so maybe it's it picks out. This infinite subsets I'm now associating with the indices, and it's always the same class. In fact, it's a clique, and this corresponds to some class I'm going to put in blue, which I'm going to call LV. This is an LV, and this is an LV. Okay. Okay. So that's by the infinite Ramsey theorem. And now I still have to make my way from the beginning into there, so that is going to be LU. Okay, there's a word which is W0 up to here W3, and that's LU. And then by construction, I have that W belongs to LU, LV to the omega. Okay, by construction now. Okay. Does that make sense? Okay. Oh, I need one more thing. Put this one up. I need one last thing. For any, so this is 3, I guess. So for any equivalence class LU and LV, either LU LV to the omega is a subset of LV, or LU LV to the omega intersection L of A is empty. Okay, so remember, this is an equivalence class of finite words, but because I'm raising it to the omega, that's now an infinite set of infinite words. I'm saying that all these words here, either they're all accepted by A, or actually none of them are. And the proof is by picture that if I have here LU LV omega, and here I've got L of A, if I had a word in the intersection, so I have here a word that's in LU LV, well, by the definition of my equivalence relation, this word satisfies the condition of being accepted by L of A, but by the definition of the equivalent words to it, they're all going to satisfy the same condition because they're going to be visiting infinitely many, lead to paths that visit infinitely many accepting states and so on. So this entire thing is sucked into L of A. Okay, so this is something one has to write out to be absolutely sure, but this is actually a simple thing. And I am now done. I can finish the theorem. So what we have is that sigma omega minus L of A, therefore consists of finitely many finitely many sets of the form LU LV to the omega. Okay, and the punchline is that I can, for each of these classes, I can easily build a Büchi automaton. When you give me a class, meaning you give me a U and a V, I can build an automaton that accepts exactly this class. That's actually, again, an exercise. So I can build the complement language as a finite union of Büchi automata. And therefore, I've shown that you can complement Büchi automata. Okay, does that make sense? Okay, so I'm going to end in basically 1 minute because I'm out of time. Let me just see. Just want to say a few words. So to kind of properly do what I had planned to do, I would need another hour, I think, or maybe 2. But it doesn't matter. I hope you enjoyed this. I just want to say that if you do want to see the results, which is the decidability that I alluded to in the abstract, decidability of, you want to see decidability of MSO over the natural numbers and powers of 2 and powers of 3, for instance. If you want to see decidability of this, so this is where you can also say something is power of 2, something is power of 3. Then I'll point you to the paper. Just want to see what the title, the exact title is. So this is on the decidability of monadic second order logic with arithmetic predicates. And the authors are Valérie Berthé, who is in the audience, Togrul Karimov, so former PhD student, Joris Nieuweld, another former PhD student, Nieuweld, myself, and then see me here, Vahanvala, who's going to be speaking later today, another PhD student, and my colleague, James Worrell. Okay. So we've covered, if you think of the Kant acronym, we've covered combinatorics. We had some Ramsey theory. We've covered automata, obviously. And the number theory actually comes in here. Unfortunately, I've not been able to show it. So here you need to, even for just a single one of them, well, so we haven't been able to leave the 60s right now, right? So to bring, I have to say there's a huge amount of work that has taken place between the 60s and now by people such as Olivier Carton, who has shown that if you add words that are morphic words, so predicates corresponding to morphic words, that's decidable. So that was a landmark result with Wolfgang Thomas. There's also work by Alex Rubinovich, by Landweber, by many people. So probably some of whom I forget. And what I meant to say is that in terms of the additional techniques that need to enter here, you need Baker's theorem in linear form logarithms, which was not available to Elgot and Rabin when they proved their result, because it was shown by Baker in the 60s. You got a Fields Medal in the 70s for that result, and it was shown like in 68 or something. And they proved they proved the result for a single one of those in 66. So they would never have been able to prove this without Baker's theorem. It's also using these tools such as Semenov's theorem. Of course, Semenov is also a key name in this field. It's using toric words, which are these kind of rotation words. So all this technology that we've seen in some of the other lecture actually all comes in to the decidability result here. So, well, you've been, I've sold you short, but if you go to the paper, then you can see the full story. Okay, thank you.
Any questions?
So thanks for the talk. So you showed in this talk that these Büchi automata were appropriate for monadic second order, for showing that monadic second order logics were decidable. So it seems, I mean, so you cannot go to higher than monadic, because otherwise your tapes would be two-dimensional, and that's maybe
it becomes undecidable.
But can you do more than second order?
I'm not the best expert here, but I suspect that if you go to third order, you will run into trouble.
So
but
there are some operations that you could not do with Büchi automata.
Oh, I mean, for sure. You would have to find another.
In the higher than second order.
Yeah, a short answer is I don't know, but I suspect not. I suspect not.
And is this the kind of, without the monadic, is this the kind of algorithms that is used, like if you want to prove a statement in arithmetic, you construct this automata and
so people have not really used this so much to prove arithmetic statements, because, and also, for instance, this is kind of new. Now you can start proving generally non-trivial statements now automatically, but this is relatively new. But where MSO has been used tremendously, and in fact, rather, these Büchi automata techniques are in formal verification, automated verification. So the model checkers that are being used by Microsoft and by hardware and software houses and by the avionics industry, the automotive industry, they use a lot of model checking. This is all based on Büchi automata techniques. So they encode specification. They have a model, so typically a Simulink model that they reduce to a finite state model with Büchi type conditions, and then to verify them, they use automata techniques. So this has been hugely influential in kind of practical verification. The arithmetic component, or adding these predicates, this is more like at this point I would say a theoretical investigation that has not really been exploited either by number theorists or by practitioners.
Any other questions? Okay, so let us thank the speaker again.